Today is Wednesday, September 20th, 2023. Come on a journey with me, a long journey, back to when you were 8 years old. It's a dark and clear night, and as you look up in the sky, it's full of magical and bright lights. What do you see? I see stars shining brightly. I see planets. I see the North Star, the Big Dipper, and my favorite, Orion with his belt. Are you wondering what else might be up there that the naked eye cannot see? When you are 8 years old, it's all very mysterious. As we come back from our journey today, September 20th, 23, I welcome you to the third session of ARCS Forward and the National Scholar Speakers Series. This is the first of 4 sessions to be held this year. Thank you for tuning in today and learn more about planetary science. I am Beth Wainwright, ARCS Foundation National President, and a Pittsburgh Chapter member. I will be moderating our session today. It is my pleasure to lead this ARCS Alumni Hall of Fame session, which has become a tradition for ARCS Forward. This is the 3rd year that we have highlighted our Hall of Fame inductee for the year. Beginning in 2001, we have heard from outstanding scientists who are former ARCS scholars. This year, our 2023 Hall of Fame inductee is Dr. Heidi Hammel. Dr. Hammel will be joined by another scholar alum, Dr. Ori Fox, to discuss the field of astronomy and Dr. Hammel's impact in that field. First, a bit of business. For those of you who are new to ARCS Forward, ARCS stands for Achievement Rewards for College Scientists. The mission of ARCS Foundation is to advance science in the United States by providing financial awards to academically outstanding U.S. citizens studying to complete degrees in STEM. ARCS Foundation has a 65-year history of furthering this mission and is a leader in scientific philanthropy. Since our founding in 1958 in Los Angeles, ARCS volunteers have been working to elevate young scientists by providing them with unrestricted financial awards. ARCS Forward is a national scholar speaker series featuring ARCS Scholar alumni discussing their work in an online forum. You will hear from our guests today about how an ARCS award helped them when they were trying to complete their education and break into the field of astronomy. On behalf of our ARCS Forward Committee, thank you for joining us today. Now, let me introduce our 2 special guests. First, I'd like to welcome Dr. Ori Fox. Dr. Fox is an astronomer at the Association of Universities for Research in Astronomy, known as AURA, A-U-R-A. He works as an instrument scientist on the James Webb Space Telescope launch and operations team. Dr. Fox is a principal investigator of several Webb Telescope and Hubble Space Telescope observation programs, working to understand the evolution of stars and their metals. Dr. Fox was a Metro Washington ARCS Scholar from 2007 to 2009. Thank you for being here, Dr. Fox. And now, let's give a very special welcome to our 2023 ARCS Alumni Hall of Fame inductee, Dr. Heidi Hammel. Dr. Hammel is a 1982 MIT graduate and was a 1985 ARCS Scholar while pursuing her PhD in physics and astronomy at the University of Hawai'i. Dr. Hammel has an extensive career in planetary science. She is particularly known for her research on Neptune and Uranus. Dr. Fox is going to talk with Dr. Hammel about some of her many research highlights. At this point in her career, Dr. Hammel is focused on ensuring the future of science. As she has said, she, quote, made a commitment several years ago to move from the doing of the research to the enabling of the research. This has always been a guiding principle for her. When gifted with 100 hours of guaranteed research time at the Hubble telescope, Dr. Hammel gave it all away to younger scientists. Dr. Hammel is the current Vice President for Science at AURA, A-U-R-A, overseeing several observatories, including the Hubble Space Telescope and the James Webb Space Telescope. Dr. Hammel has also been recognized for her commitment and skill as a science communicator, receiving the Carl Sagan Medal from the American Astronomical Society's Division for Planetary Sciences for outstanding communication to the public. Discover magazine has called her one of the 50 most important women in science, and she even has an asteroid named in her honor. Please welcome Dr. Heidi Hammel.
Thank you.
And now, Dr. Fox, we welcome your conversation with Dr. Hammel.
Okay. Hello, everyone. Hello, Dr. Hammel. Would you like me to call you Dr. Hammel or Heidi?
You can call me Heidi. I'll be
Okay.
informal here. Thank you.
Very good. Well, it's great to be chatting with you virtually. I know that Beth is going to be asking you some questions about your career and specifically the impact that ARCS had on it after we talk a little bit about the science. But I think at least to get everybody warmed up, maybe it would be useful if you could just tell us a little bit about your background and how you specifically got interested in solar system planets and the James Webb Space Telescope.
Sure. Well, as you heard in the intro, I was a student at MIT, and I had a great mentor there. My professor's name was Jim Elliott, and he was strongly supportive of everything that I wanted to do. And his specialty was studying planets and using a technique called stellar occultations, where you watch planets cross in front of stars. And as the planet or asteroid or whatever it is crossed in front of a star, you learn things about that object. So I worked with him on that while I was an undergraduate. But when I went to graduate school, I thought I would get a degree in astrophysics, broaden my horizons to the edge of the universe, and learn about galaxies and stars, stellar interiors, cosmology. And that was really interesting. But when it came time for me to focus and write my PhD dissertation, I went back to planets. At the time, and this was in the mid-1980s, at the time when ARCS was supporting me in 1985, we had not yet flown a spacecraft past the planets Uranus or Neptune. And so they were mysterious. And they were the topic of my PhD dissertation because I wanted to learn as much as possible so that we could do a better job planning for those spacecraft missions. So I was the world's expert in making observations of Neptune, Uranus. And after I finished my PhD in 1988, I was invited to the Jet Propulsion Laboratory in Pasadena, California, to join the Voyager imaging team for the Neptune flyby. This was like amazing. That was like, the pinnacle of what I could even imagine, to be able to actually fly a spacecraft past the planet that I had spent years trying to study. It was hard back then. We didn't have Hubble in 1989. We did not have the Keck Observatory or the Gemini telescopes. All the powerhouse telescopes of today hadn't even been invented yet at that point. So it was amazing to participate in that. And I loved planetary exploration. I loved, even when I was doing it with telescopes, I loved the sense that we were explorers of other worlds. And so I kind of kept that all the way through. Once Hubble was launched and once it was repaired, I used it to follow on the Voyager Neptune observations. I used it to study Jupiter when a comet was crashing into Jupiter, many other science projects. But I knew in the 90s that there was no mission to Neptune. And so I decided that I would participate in the building of the next generation of space telescope after Hubble. And that is what evolved into the James Webb Space Telescope after more than 20 years, 2 decades of work with NASA on that program. But boy, has it been a spectacular opportunity now to see the science of JWST finally coming to fruition after decades of planning. So that's a little snapshot of kind of how I got where I am. Oh, you're muted. I can't hear you.
I'm sorry. So I know we had some pre-listed questions, but I'm going to go a little off script because you brought up a lot of really good ideas in that answer. It's interesting to note, I actually spent a summer researching Jupiter at JPL with a scientist there named Glenn Orden. Maybe you know him.
Oh, we know him very well, yeah.
And I was there. Well, Cassini was around for a while, but I was there when Cassini was. It was just early 2000s, and so I think Cassini had just arrived at Saturn, and some of the first images were coming in, and it was really a spectacular time to be there. You grow up and you think these planets are so close and that we already know so much about them, but then it's amazing how we keep learning more and more even today. Even after the flybys, there's still so much more to learn. So one of the questions that I thought the audience might be interested in is a good segue into JWST is we have had these flybys of almost every planet at this point. We've seen these planets in excruciating detail. So the question is, what does JWST offer that a lot of these flybys may not have been able to probe? Can you talk a little bit to that?
Yeah, I can talk extensively to that. The hard part is going to be reining my answer in. So maybe I'll give you just like tidbits from each of the giant planets. That's what I study: Jupiter, Saturn, Uranus, and Neptune. For Jupiter, it was one of the first images taken with James Webb Space Telescope to demonstrate it could look at bright objects. And the most surprising thing from the JWST imaging of Jupiter was on the shadowed edge of the planet, which should have been dark, there was a bright line. And it shouldn't have been there. They'd never seen anything like that before. After a lot of debate and discussion, the team is kind of landing on this idea that might be ionospheric glow in the upper atmosphere of Jupiter that we have never had enough sensitivity to see before. It glows at specific wavelengths in the infrared, which is what JWST uses. And we had never seen it, not with the half a dozen spacecraft that have flown by Jupiter. There's an orbiter there now, Juno, but it doesn't look at these wavelengths. Galileo didn't look at these wavelengths. So, a brand new discovery in sort of the very beginning of JWST's operation for Jupiter. For Saturn, we just had a paper come out last week. So people can, if they want to look at my Twitter page or Facebook, you can see links to these new images where we're studying infrared glow in the atmosphere and even in the rings of Saturn. And we are able to sense chemistry with better sensitivity and spatial resolution than even Cassini could do. Cassini did have an infrared instrument, the Sears instrument, but at certain wavelengths, JWST, being a very large telescope, has better sensitivity. So we're learning new chemistry. So even for Saturn, even though we orbited with Cassini for 17 years, we are learning new things with the James Webb Space Telescope. I remember when the Uranus image came down, I saw it for the first time. And I was just so excited because, Uranus, the planet, I've looked at that a lot with Keck, with Hubble, and I knew what to expect there. What was remarkable was the rings. The rings just sort of shone out beautifully in the Uranus image. And we know that these rings are evolving with time because we've been able to sense them with Keck and Voyager. So Voyager in 1986, Keck was able to detect the faint rings at one moment in 2007 when the rings were edge on to us. And now with JWST. So we will be able to study the rings and how they evolve with time in ways that were impossible prior to the launch of JWST. And then finally, Neptune, probably my favorite planet. Uranus is a close second, but when I saw the first picture of Neptune and its ring system, I actually started to cry. Like, this is so amazing. And then I started jumping up and down, and my mother's like, what's wrong? Are you okay? And I'm like, it's fine. Come look at this image. I held my cat up to the screen. Look, it's Neptune with JWST. The cat didn't care. What we saw were faint rings that we knew were there from Voyager, but we had not been able to see them for over 33 years. They were just beyond the limits of even our most powerful telescopes, like Keck, like Hubble. And there they were, just boom, sitting right there, super easy to see. And we know that they have changed with time. So, remarkable science will be coming from JWST. And that's just the 4 planets that I study the most. Every aspect that JWST has turned its sights on is making new and remarkable discoveries, both within our solar system and all the way to the most distant galaxies in the universe.
Great. So I see a hand up. I don't know if that's intentional from the ARCS meeting Zoom. Did somebody want to say something? It was not intentional. Okay. So that was a great introduction to the solar system. I'm debating where to go with this. I think maybe for the audience out there, we can talk. We'll take a pause from JWST and talk a little bit more about the solar system in general. Maybe you can tell us why do we study the solar system? What do we learn from it? And besides the obvious, the planets, what are some other objects that we like to study and that JWST will be studying?
So the solar system is our home base. It is our local neighborhood. And to understand how planets work, and we care about how planets work because we live on one, and we want to understand how atmospheres interact with surfaces, how atmospheres can change with time. We only are experiencing our own Earth in the moment that we're in, and with our historical record. But the other planets in our solar system offer test beds for other processes, other pathways that may have led planets to form in the way they do. So, for example, why does Venus, like our near-Earth twin, right, have this thick, extremely hot atmosphere? We think it might have been a runaway greenhouse effect sometime in the past. But what were the conditions that led to that? And can we learn something from that to prevent something like that happening here on Earth? That's really a good question. What about Mars? It's about half the size of Earth. It's a good sized planet. Its atmosphere is extremely thin. At the moment, it is extremely dry. Has it always been that way? Is it possible that at some point in the past, there was liquid water on that surface, that there was more water available? And if so, does that mean that life could have thrived there at some point in the past? These are the kinds of questions that we like to explore in planetary science. We also, in addition to the planets themselves that we've talked about, where there's huge swarms of other kinds of bodies. There's the asteroid belt, hundreds of thousands, if not millions of asteroids that orbit the sun between Mars and Jupiter. But there are also many asteroids that orbit inside that, orbit near the Earth. We call them near Earth asteroids. And these do hit the Earth, and so that could be bad. If a really big one hit the Earth, that could be really bad. And so part of what we do in planetary exploration is we devise tools to be able to measure all of these asteroids, make sure we've identified them, make sure we understand their orbits and their characteristics. A lot of what we do in astronomy, in planetary astronomy, is remote sensing. Right now, we're on the verge of having pieces of an asteroid returned to the Earth. That's the OSIRIS-REx mission. It took samples from an asteroid called Bennu, and in about a week, a couple of days, anytime soon, I don't remember the date, but it's like really soon, we're going to have these samples of this asteroid back on Earth, and that will allow us to study its composition, its densities, of what this material is, and that will help us understand what might happen if one of these larger asteroids happens to be on a collision course with Earth. So we call that planetary defense. We care about that a lot. And then at the other end of our solar system, out beyond Neptune, we have Pluto and what I call 10,000 of Pluto's closest friends and relations in what we call the Kuiper Belt. These objects are beyond Neptune. They're called either Kuiper Belt objects, sometimes trans-Neptunian objects. What's exciting about these objects is that in their distribution, they actually bear a record of the history of our solar system and how it came to be the way it is today. Our solar system today, the positions of the planets, is not how they were when they formed. And it has evolved. And that record of the evolution is captured in the Kuiper Belt. So, so whether we're exploring planets to ask the question of could life exist elsewhere in our solar system, how do we protect life on our own planet, how did our own planet even come to be with life on it? All those questions are why we do planetary astronomy. It's a pretty big remit.
Oh, those are all very good reasons. You've written your fair share of proposals, I can tell. So, okay, so now let's go back to JWST, and I want to talk about your research in just a moment, your specific research. But as many people probably know, JWST was not a short-term project. It has been going on for, I would approximate, about 30 years. And of course, it was a $10 billion price tag, which some people say is expensive in the grand scheme of the national budget. I would say it's actually, about a drop in the bucket. But that said, we don't have to talk politics. I'm more curious, after all those years of investment, I shared the same experience. So much of our careers and our expectations were really looking forward to JWST results. And it all came down to a single launch on a Ariane 5 French rocket, which has a very good track record. But nonetheless, there are always risks involved. And there's all sorts of behind the scenes stories that the public may have heard along the way about the transportation process and the final attachment of the telescope to the rocket. And then there was launch day itself. So I was hoping you could maybe walk us through your experience in the months and the weeks and the hours, minutes, seconds before launch, and how you felt, where you were on launch day, and your personal feelings once you saw the launch was successful.
Yeah. Gosh, I started working on that project more than 20 years before the launch. So, but let me just talk about the launch itself, because, as you said, those of us who worked on this project, we spent decades planning, like watching it go from PowerPoint concepts or cocktail napkin writing to PowerPoint, to requirements, to hardware, to an integrated spacecraft, then put on the rocket and then launch. So for the launch day itself, I was at the Space Telescope Science Institute in Baltimore, Maryland. That's where mission control for James Webb Space Telescope is located. And it was, it was COVID, COVID was like huge. Everybody was in masks. It was extremely limited because COVID, we couldn't have people coming, couldn't tour. But there was a small group of people that were there at Space Telescope in the auditorium. And I was so nervous. I could not sit down. I was standing at the side of the auditorium. I was pacing. I was like, because I was, this incredible spacecraft that we had spent all these years and years building was now on top of this rocket, and they're going to light the fuse. And rocket science, the reason we always say things like, this isn't rocket science, or, that rocket science is hard, it's because it is. And you never know. When you have a launch, one wrong thing happens, boom, it's gone. So it was really nerve-wracking. So when it did launch, we're all like, okay, we got off the ground. But then, there's a very complex series of steps that need to take place. Once you launch, that's great. But you also then have to separate the fairing from the main rocket. And so, you're waiting. Did separation occur? Yes, it did. Woo! And it was right on time. So then it's like another, breath of relief. But then with JWST, then we do have a video of our last view of it as it separates from the fairing. And the first thing that we saw in this video that was taken from inside of the fairing was the deployment of a solar panel. But that happened like 3 minutes early. And we're like, oh man, what is that? It's too soon. What's, something wrong? Well, it turned out that launch was so perfect that the rocket and the trajectory, they were on the right trajectory. They didn't have to do any course correction to be on a different trajectory. So the solar panels was like, okay, I'm in the right place. I'm going to deploy. So everything was perfect. So, there was nervousness. And so, at that point, we knew we had a spacecraft en route to where it was going. But this telescope was so big. There's a little model of it behind me there. It has this sun shield that's the size of a tennis court. The mirror itself is so large, the mirror had to be segmented and folded up to fit inside the rocket. And all of the unfolding had to happen. And that took a month, a literal month. And I had a checklist. A to-do, James Webb Space Telescope to-do list, and it was like every day what deployment was going to happen, and it's just checking them off. And there were some that were really scary. The most frightening one, the ones that I was worried about, was the secondary mirror. This is the thing that allows the light to focus in on the instruments. And if that didn't deploy properly, we had nothing at all. And so when that one did deploy and locked in place, I'm like, that was the moment. That was about like a few weeks after launch. That was the moment where I actually started to feel like, oh, okay, this is all going to work. It's going to be good. And now, even when we got to our location at the Earth-Sun Lagrange 2 point, there was still months and months of work to focus all the segments together, to verify all the instruments were working. And all of that, was all before we could take our very first picture with Webb or get our first spectrum with Webb. So it was 6 months of waiting. And because you're involved in this as well, that was a long 6 months to be a scientist. I'll just share one last thought. I spent 20 years like advocating for JWST, like, arguing for it, planning for it, developing white papers about it. And then after it launched and started that deployment sequence, there was this period of time when I was kind of lost because we're done advocating. I mean, it's in space now. And I'm like, we hadn't started doing science yet. So I hadn't slipped into like the science mode of like getting data and analyzing it. So there was this long period where I was adrift. It was a weird emotional feeling that I just didn't quite know like what to do. I I'm done advocating, but I haven't started being a scientist yet. So it was an odd time. I don't know if you felt that as well. I imagine other JWST scientists had similar feelings, but I just share that because people sometimes don't think of scientists as being like emotional people, but we really are. And that was a weird emotional time where I was happy that we were done launching, but I wasn't starting the work yet. And it was just peculiar.
I hear you. And for me, my data were scheduled to be taken at the very end of the first cycle. So I started seeing all my colleagues getting data, and I'm just sitting there twiddling my thumbs. I mean, I actually wasn't. Don't tell my boss that. But no, it was frustrating seeing everyone getting data and being like, when do I get to jump in on this? But now all things are good to go. And we have a lot of exciting results. And that's actually a perfect segue into the next question, which is just last week, as a matter of fact, the Space Telescope Science Institute hosted the 1-year anniversary party. That's what I called it. They called it the first year of JWST data conference, where all the teams got to present some of the research highlights from the first year. And there were many, many exciting results, specifically a lot of high redshift galaxies. That's really one of the primary reasons that JWST was built. Exoplanets, we may not have time to touch on that today, but when JWST was being built, there was 0 exoplanets known. I always love this fact. Exoplanets was not a large part of the JWST program. And then Kepler came along, and the technique for discovering these planets really improved over, the mid-2000s. And Kepler came along, and by 2000, well, I forget my exact timeline. In 2010, there may have been around a dozen exoplanets known, and now we have 5,000 exoplanets known. And the limit, the amount of knowledge of these exoplanets is almost 0, and the amount that we can learn is practically limitless. We all have our imaginations of Star Wars, Star Trek. What could be on these 5,000 exoplanets, and we're the numbers is growing exponentially. So there are all sorts of worlds out there, and a lot of the conference focused on some of the first spectra of these worlds and what molecules and chemicals exist in these worlds. So it's really fun to start imagining all of that. And of course, I was telling you before today's talk, I study supernovae explosions. When a star reaches the end of its lifetime, it explodes and it produces all sorts of materials. And JWST, for the first time, can really start to study some of the dust and metals that are created in this explosive process. But of course, getting back to your research, there was a lot of focus on, as mentioned in your introduction, this 100 hours that you gave away to these younger students, and a lot of really cool observations. I was hoping you could tell our audience a little bit about your specific research program and the results from your team and these students.
Yeah, absolutely. Back in 2002, NASA had a call for proposals for scientists to serve on the science working group for what was then, at that time, called the Next Generation Space Telescope. And I wrote a proposal for that and brought in like co-signees of dozens of planetary scientists saying, while I know this telescope is being built to see the first galaxies that ever formed in the universe, it will also be able to do fantastic solar system science, studying objects in our local neighborhood. And that proposal was accepted. And so in 2003, I was selected as an interdisciplinary scientist for the what was then renamed James Webb Space Telescope project. And as an interdisciplinary scientist, you were guaranteed 100 hours of time on the telescope, and you were permitted to use any of the instruments. That's what the interdisciplinary part was referring to. Each instrument team got time with their instrument, but only the interdisciplinary scientists got time with all of the instruments. And so So decades roll by. My career evolved, and I moved from being an active astronomer to someone who is actually, as we said in the introduction, facilitating astronomy. I'm now vice president for science at AURA, and we work on managing giant telescopes and building new telescopes. But I had my 100 hours guaranteed, and so I worked with my planetary science community to develop projects, and basically gave away my time to lots of people to create effectively a solar system sampler. What is the brightest thing we can look at with JWST? It's Mars, and we did. What is one of the fastest things, like fastest moving in the sky, that we can track with JWST? That turns out to be asteroids, and we did that for the DART mission, the Double Asteroid Redirect Test. We actually tracked that with JWST. Also, what are some of the more challenging faintest objects in our solar system, the distant Kuiper Belt objects? Pluto's a bright Kuiper Belt object, but there are hundreds of smaller ones, fainter ones. And so this program that I developed, with all these young people is, a sampler of everything. We can't do a deep dive into everything, but we wanted to demonstrate what the capabilities of JWST were. And we even did an occultation. You remember that I mentioned that with Jim Elliott with the stars? Well, we actually used JWST to watch a little rocky body called Chariklo cross in front of a star. And we're able to learn about its surface chemistry and about Chariklo's double ring system with JWST. My goal with this science time was to entice the community, to demonstrate all the amazing capabilities of JWST. And, there were surprises. I mean, like the rings of Neptune popping right out. That was a surprise. Another thing that was surprising was looking at Saturn's moon Enceladus. The Cassini spacecraft had found Enceladus has plumes of material ejected from its south pole. But with JWST, what we were able to image, not just the moon itself was so tiny we could hardly see it, but the plume of material we discovered extended for thousands and thousands of kilometers, dumping just huge amounts of water into orbit around Saturn. And so it was surprising how huge that plume was. So there was just a remarkable amount of data that is still coming out. As I said, papers are, we've had only a few papers actually come out yet, because it takes a while. The sort of like, and you know this because you're an astronomer, our standard time between getting data and publishing it is typically about 2 years. And so to be able to get all this data out within the first year has been really challenging. But it's been such great data that people have gone for it. So Titan, Saturn, Mars, I think the Europa is about to come out. So pay attention. Very soon you'll hear about Europa observations with JWST. Enceladus. It's all starting to come out now into the public sphere. It's a really remarkable time. And what makes me most happy is seeing all of these other scientists just raving over their data and just learning new things. I had an email yesterday about some topic that I'm not going to tell you what the details are, but what they said was, this line has never been observed before in nature. Discovery, that level of discovery is happening with JWST data, whether it's solar system or exoplanets, dust, galaxies, and even the early universe. It's what an amazing time, and really, really exciting.
That's great. So we are at the end of time. There is a question online, and I had one more fun question, just in case anyone thinks that I could have forgotten to ask Heidi this question. Don't worry. It was always in my back pocket. It's a little bit of a joke, but it's actually a pretty serious question that a lot of scientists take more seriously than the public actually thinks we do. And that is, have we found life in our solar system? And are we actively looking? And what are we looking for?
Yeah. So you mean life beyond Earth, of course, because life
Well,
is
we're
here
on
in
Earth.
abundance. We are looking very closely at in our neighborhood. I mean, part of the reason that we're looking so closely at Mars is because there is evidence that there may have been liquid water on the surface of Mars at some time in the past. And that may mean that there could have been conditions there that are conducive to life forming. And there's no evidence yet for that. No evidence that has stood up to the test of the scientific process. We'll put it that way. We had a little kerfuffle with a meteorite called ALH 8401, where people thought there was evidence for life in that meteorite, but the bulk of the scientific community afterwards, like, no, no. So another place that we're looking very seriously within our solar system is the moons in the outer solar system, Jupiter's moon Europa and Saturn's moon Enceladus, and some of the other large moons, because the evidence we have from our spacecraft, our orbiting spacecraft, is that under the icy shells of these moons is liquid water oceans and rocky cores in their centers. And so we also know that there's energy sources in these moons in the outer solar system based on their interactions with other moons. So again, you have the ingredients for life, we think, in these moons. So the Europa Clipper mission is going to be launching, I forget the date, the end of next year, soon. It will go to Jupiter's moon Europa and map out the surface and look for places that are potentially interesting for us. As I already said, we used JWST to look for this water plume on Saturn's moon Enceladus. So in our solar system, there are intriguing places. And I also will note that exoplanets, of course, are intriguing as well. There's different kinds of exoplanets that orbit different kinds of stars. JWST was not built to look for life on other worlds outside our solar system. As you and I, we know this. Like you said, we didn't even know of these. That last I checked, 5,502 exoplanets known. And JWST, while it'll do a great job studying the biggest exoplanets, it's trying really hard on the Earth-like planets around M-dwarf stars like we see in the TRAPPIST-1 system. It actually is probably not going to be the tool that finds evidence for an Earth-like world around a sun-like star. That needs a bigger telescope. It needs some different technology, and we've actually started working on that already. NASA has put together a concept called the Habitable Worlds Observatory, and it was a top ranking in our community's decadal survey. The teams are now stood up for that, and just as of 2 weeks ago. And so that's where the future is, I think. So we're always looking forward. We are the generation that can find life on another world if we put the resources into doing it. We do have the technology to do that. And so we're very excited about that. I'm excited about that.
So am I. On to the next thing already, right? It's already been 1 year for JWST, bigger and better. So, yep. Well, I am out of time. So I wanted to thank you very much for giving us that deep dive into our solar system and JWST. I learned a lot, even though I knew a lot already. I learned a lot today, and I think our audience did as well. So I'm going to turn it back over to Beth, and you can field, or if you want me to, I can, but there are some questions online, and you can tell me, or you can handle it either way.
You're muted, Beth. You got to unmute.
Thank you very much. This was fascinating. And I will follow up with the one question that is online, Ori, to which you referred. The question is, I recently read that data from JWST is causing scientists to rethink the age of the universe and how it was formed. Can either of you or both of you comment about this?
So I'll go first, and then Ori can correct me if I say anything wrong. We built JWST to look at the earliest galaxies that ever formed in our universe. That was its purpose. We called it the first light machine back in the early days. And its goal was to examine those earliest galaxies that formed after the Big Bang took place, after the universe started to form, materials in the universe, and stars started to form, and then galaxies started to form. And what we have found is that these earliest galaxies with JWST seem to be brighter than our models would have suggested. They seem to be bigger than our models would have suggested. And they seem to have more well-defined structure than we would have anticipated. So it's like we built a telescope to see a baby picture of a galaxy, and we found a teenager instead. And so there's this discrepancy of what that is. And what I will share with you is that is awesome, because it means we're going to learn something. It means there's something in our theories that are not being replicated by reality. And so we are going to have to do a deeper dive into our understanding of the physical processes as we understand them in the earliest universe, and question whether we've properly accounted for everything, because it seems we haven't, because what we're seeing with this new telescope is not aligned with our expectations, and that misalignment is where the science happens. So I read some of these articles about, well, this is the end of cosmology as we know it. We have to change our fundamental understanding of physics of the early universe. Yeah, but we may not need to change physics. We may need to change our understanding of how the physics is manifesting itself in the earliest universe. But we don't know that yet. We have the misalignment. We're like this, right? We're not aligned. And so it's going to be a very rich topic in astrophysics in the coming years. Did you want to add anything to that, Ori?
No, I mean, you summarized it perfectly. And all I can say is, I want to just reiterate, this is exactly why we invest in these things. This is an interesting result that in itself is worth the $10 billion. I mean, instead of just extrapolating the line that we had observed with Hubble out to larger distances and assume that was going to be correct, we are learning really new things about our universe. A lot of times, I do hate to say it, I don't want to be, the party pooper. Another way of saying what Heidi said is chances are the explanation is pretty boring. Maybe we misunderstood, the way extinction works.
That's how dust blocks out starlight. Yeah, extinction is
exactly. Yes.
Right. Yeah. Maybe we don't understand how dust forms interacts with materials in these primitive galaxies, and so we're miscalculating something. I mean, we don't know yet. That's what we're going to find out. Yeah.
Yeah, but everyone's actively working, including myself. I'm already writing a proposal for the next cycle to study this exact thing. So it's very exciting to be a part of this, time. Yeah.
Yeah. Oh, thank you both for that. There is another question in the chat box, and it is, could you talk about the concept of time as it relates to the images we're seeing from JWST? Is it true we're actually looking back over 13 billion years in time?
Yeah, this is true. Let me start locally. When you look at your hand, the way you see your hand is like light from the light bounces off your hand and into your eyes. And that, the light travels at the speed of light. So it's almost instantaneous over a short distance. But when you go over a longer distance, that speed of light becomes relevant, And so I'll give one of my own personal examples that I know is when I was studying Neptune, at the same time that Voyager was flying over the Neptune cloud tops, the light from Neptune took 4 hours to come from Neptune back to the Earth. So I was looking 4 hours back in time when I looked with a telescope on the Earth, compared to the spacecraft, which was at Voyager. And I had to account for that when I was trying to do comparisons of telescope observations with Voyager data. Now imagine a nearby star. You've heard the term light year, right? That's how far light travels in a year. And the closest star to us, Alpha Centauri or Proxima Centauri, is like 4 light years away. So anytime you look at Proxima Centauri, you're not seeing it the way it is right in this moment. You're seeing how it was 4 years ago. And then going even further, the nearby galaxies, they're tens of thousands of light years away. And you can even see galaxies that are like, millions of light years away. Imagine a galaxy that's 65 million light years away. The light from that galaxy, emitted from that galaxy at the same time that dinosaurs were roaming the Earth, but it's taken 65 billion years to get here. And so James Webb Space Telescope, it was built to see the earliest galaxies. And as we've been talking about here, how early is early? Well, it's like 13 billion years, 13.1, 13.4, 13.6 billion years ago that those galaxies formed, but the light has been traveling to us on Earth all this time. So all of our telescopes are time machines, but JWST is like the best time machine we have ever built. Well, okay, now I'm going to make sure that my friends who study with the Kobe spacecraft and Planck, there are some kinds of telescopes, specialized telescopes, that are actually looking at the signature closer to the Big Bang than we can see with the James Webb Space Telescope. They would argue that they're the best time machines ever built. But JWST is built to see the first galaxies that formed. Anything else, Ori, you want to throw in there?
Nope, that was perfect.
Yeah, we have one request, but I don't think we can handle it today. It's ask Heidi if you could show your favorite photo from Webb or any other telescope. Perhaps maybe that would be something we could send out after our session today, since we're not really set up to do that today.
Yeah.
So if I may, I'd like to shift a little bit in our conversation and talk with you about your career and some of the accolades you have received. So my first question is, of all the things that you have done and have been recognized for, of what are you most proud?
Well, I would say it's hard for me to answer that because I've done a lot of different things. I think in this moment right now, being on the front lines of JWST and advocating for the solar system work that we're doing now that has enabled, all these, early career scientists to get this new data, I'm really proud of that. That was, I think that was great. I'm proud to have taken part in that. And ensured that this, I played a tiny piece of the story of helping to build JWST and helping to share the information about JWST. And I think a more general comment, I'm really proud of the communication work that I've been able to do over the decades that I have been an astronomer. We need people who can communicate the wonders of the universe and why it matters and what's important. And it's something that you have to learn. It's a skill. And so by example, I hope that I've been so happy to see on the new social media of today, things like TikTok and other kinds of social media, a lot of young women actually getting out there and sharing their science in an enthusiastic way, in an accessible way. I sort of feel like I was kind of a leader in that. And so I'm proud of that as well, communication of science.
So that kind of leads me to my next question, because when you were in school, there were only about less than 50% of women, of all scientists were women at that time. Can you tell us about some of the challenges you might have faced while you were a minority in science?
Yeah,
And how did this shape your career?
less than 50%. Wouldn't that have been lovely?
Yeah. Well, yeah.
Yeah. When I was a student at MIT, an undergraduate, it was less than 10% of the.
I'm sorry, I missaid that. I misspoke. Today it's less than 40. Right.
Yeah.
Yes.
Yeah. And so that was it was very difficult because it was difficult in many different ways. People didn't think women could even do science. I would give talks and I'd have people say, I didn't even know women could do this. I'm like, well, yeah, they can. There was, I was fortunate in that I came a little bit later. I wasn't on the very front line of women. People like Vera Rubin and Margaret Burbidge, they weren't even allowed to use the telescopes, right? Because women weren't allowed to do that. By the time I came along in the 1980s, we'd moved past that. We were allowed to use the telescopes, but our numbers were so few that we were like oddities, and people just didn't. It's hard to explain. There was just so many what we today call microaggressions, where people just assume that you're not an astronomer. Like if there are two people in an office, someone walks in, they would assume I'm the secretary and that the other person was a scientist. I mean, that kind of thing, that happened all the time. You got used to that. It was very difficult to and when I was in grad school, I failed my qualifying exams the first time. And I got comments like, you don't seem dedicated enough. Like, what does that even mean? How do you quantify that? It was challenging, and the support I got from the ARCS Foundation was actually really helpful because it acknowledged that I was like being a student of science and that I was legitimate, and I wasn't just like someone who's an interloper. It was such an important thing for me at the time in the 1980s. I remember in the 1990s, we had a meeting of the American Astronomical Society. We had a committee on the status of women in astronomy. And I remember this meeting where people are like, well, women can now use telescopes and stuff, so we don't need this committee anymore, do we? And I'm like, oh my gosh. Yes, we do. We've gotten past the overt discrimination of women. You can't say you can't have telescope time because you're a woman. But there are still many, many barriers that are they're unconscious barriers. And so we're not done yet. And I'm only talking about women. Now, the whole question of bringing in underrepresented groups, they're at where we were like 30, 40 years ago. There's so much work we still need to do in science to make our field open and equitable to anyone who wants to become a scientist. So yeah, I'm going to stop there.
Well, thank you. Ori has a response in the chat box for everyone to read. I'm not going to read it now, and it includes a link for more information, so be sure to look at it yourself. Well, thank you for your talking about your ARCS award and the importance of it to you at the time that you were in school. That was going to be my next question. So I'm going to move on to a little bit different kind of question. In your opinion, how can ARCS best continue to promote science in America?
So, the work that ARCS does, recognizing and supporting young scientists is incredibly important. So absolutely continue doing that. I think that, making sure that the lens is broad enough to include the underrepresented groups, people who have not traditionally been a part of the science conversation, it's crucial to bring their voices in. They have different lived experiences that allow them to think about science in a different way than people who have been traditionally trained in the field. We know this in astronomy. We have a lot of conversation in astronomy about our use of land and who it belongs to or who it did belong to. I think having a breadth of voices is so important. And many, like me, when I was a young person, you doubt yourself, you doubt what you're doing and whether anyone notices, and are you even supposed to be here? I think support of organizations like the ARCS Foundation can really help broaden the base and broaden our field, all of the fields of science. I'm not talking about just astronomy. I'm also talking about biology, chemistry, mathematics, technology, computer science. All of these are areas where we need the full population supporting the exploration that we do in all of these fields. And so ARCS is a huge part of that. And Ori, you are also an ARCS scholar. I'd love to hear your thoughts on this as well.
Yeah, I mean, so much of that resonates with me. In life, a lot of people are insecure, very unsure about their way forward, and funding in many fields, but astronomy in particular, is tough. And so when you're a grad student and you're faced with trying to find your own way, even with an advisor, the advisors are normally very busy and preoccupied, and it's hard to get their attention. And so, really figuring out how to sell a project, how to get grant money, how to support yourself, how to sell your project to others. It's not a straightforward process. And I don't want to say that ARCS is necessarily easier to get, but it's more accessible than some of the very large NASA grants, I guess is a way to say it. And it comes with a very personal touch. And the personal touch goes a really long way. Having the ARCS members visit the schools, really tour the labs, be interested in what you're doing, host you for a free lunch, invite you up to the national academies. It really makes you feel like your work is valued, and the fact that it's integrated with other departments, not just astronomy, makes you feel like it's valued outside of just your immediate field. And all of these things really are inspirational to grad students trying to find their own way, and I think gives them some of the confidence they need to move forward. It did for me. And, I really don't think I would be here today if it weren't for ARCS, quite honestly. So I'll leave it there.
Thank you for those comments, making us feel very good in what we do and how we support science. I have a very personal question, Heidi, about what age did you decide that you were going to be a scientist? And how did you get into your field?
Well, I'll tell you, it came really, really late in my career. And to give you an example of that, when I went to MIT, people said, "What are you going to do at MIT?" And I said to them, "Well, maybe I'll be an English major." If you know anything about MIT, you don't go there to be an English major, but I didn't know what I wanted to do. And my mom tells this story of like when we were freshmen at MIT in like the first week when the parents were bringing their kids, we had the opportunity to meet the president of MIT. And she tells the story. I don't remember this. My mother says that, she was with me in the line, and the president of MIT, then Paul Gray, said, "So nice to meet you. What are you going to do here at MIT?" And I said, "I have absolutely no idea, but I think it'll be interesting and fun." And my mother said she was like dying 1,000 deaths. Oh my God, why did she say that? But the president of MIT said, "Well, that's a great attitude. I'm sure you're going to do well here." So he wasn't entirely correct about that. To me, my undergraduate days at MIT were horrific. It was the most devastating experience of my life. And I only stuck it out to shame my high school chemistry teacher, who wouldn't write me a letter of recommendation because I said I would never get in. And then when I did get in, he said to me that it was only because I was a woman. They had quotas to fill. And so by golly, I was going to graduate from MIT just to,
Just
motivated by anger. I'm one of those people, when people say stuff like that to me, I'm like, I'm going to prove you wrong, buddy. It was hard though. MIT was really hard for me. But I managed to make it through. So that was,
that's interesting.
A lot of tears involved, but I made it.
Right. So I have two granddaughters, one 13 and one 8. What advice would you give to young girls like them to get them interested in science?
Yeah, so I realized I didn't actually answer your question. I got into astronomy because I took an elective course in astronomy with Jim Elliott, and he was so wonderful that he convinced me to become an astronomer, and that was how I got into astronomy. It's not clear to me that what we need to do is encourage people to get interested in science. I get asked this question a lot. And, what was the most important course you took as a kid or in high school to prepare you to become a scientist? And my answer, to the dismay of all science and math teachers everywhere, was chorus. Chorus. We had a really great chorus teacher who taught, she was a former Rockette in the Radio City Music Hall, and she taught us, even in high school, how to be good performers and how to do professional presentation of what we did. And it wasn't so much that it was about chorus, but it was like she brought the best out of us. And so when I talk to kids, it's like, you need to find what it is that personally interests you the most. Many young people will be interested in science or math. If they're the kind of kids who love to solve puzzles, then science is the field for you, because that's what we do in science is, we solve puzzles all the time, or we do exploration of new things. If you're an explorer, if you're a puzzle solver, if those are the things that really excite you, then you should get involved in more activities that'll take you down that path. If you're a kid right now and you really, really want to be an astronomer when you grow up, you gotta do your math classes. The math is the language of science. You've got to, but you have to study your vocal skills and your written skills, because Ori said this earlier. Part of becoming a scientist is learning how to present your ideas, how to get grants, how to get funding. You need to do all that as part of science. So, I would say for your, these young women, 8, 10, find out what it is you want to do. Focus on your schoolwork, all aspects of it. You don't know yet which are going to be the most important. When you get a great teacher, run with it. Focus on what that teacher is teaching you, not just the subject, but what the teacher is teaching you about life and about how you handle yourself. And that is how we're going to get the best scientists, mathematics, engineers, technologists. That's how we're going to do it, with great teachers. So anyone out there who's a teacher, thank you, because you are the spark. You play the key role in getting people moving forward.
Your enthusiasm is so engaging, and it's just so much fun and interesting to listen to you. I do have one question that came from a member of our audience. What picture are we looking at behind you?
Behind both of us.
Ah.
Yeah. So this is a piece of the big nebula collection of dust and gas. And they call this the cosmic cliffs. This is a JWST image, one of the beautiful images that they released early on. And in this image, what we're seeing is the interaction of starlight with dust and the creation of new stars in those dusty clouds. But this is actually Ori's field. So I'm going to have Ori, you can tell him even more than I just told him. So.
Yeah, as you can see, I have the same picture behind me. It was the first image that came out, so we all quickly made our gear, and we knew there would be other good pictures, but we didn't know how good. I wish I had waited. Snapfish isn't that cheap, but now I have like a whole backlog of like 30 images I want to do pictures of. But anyway, one thing at a time. So this is the Cosmic Cliffs, as Heidi said, and this is a region of active star formation. It's a stellar nursery. And what happens, and this is really why dust is one of the key parts of, studying astronomy, which is, produced in a supernova explosion. It's because dust is what's essential for cooling down gas so that it starts to collapse under its own gravitational weight and produce a star. And when that star forms, it then glows very brightly, and it has this radiation pressure from the star itself. You hear solar winds. You also have actual winds that are coming off of the star, and it's moving material away from the star itself. And what's going on here is you have this very active region where stars are being born, and they are pushing this gas dust away from it. And what's amazing is we've been studying this region for decades. It's not a complete surprise. We knew we wanted to point JWST there because it is such a beautiful region. But if you go back and you do a time lapse with Hubble data and other data sets, you can see this dust receding. It's actually getting pushed away. It's getting swept away by these winds as the stars are burning bright and pushing that envelope backward. So it's a very dynamic scene, but it also contrasts the incredible different sensitivities that JWST has to both stars and dust. So you're seeing that color contrast, and the colors that they chose really bring that out, and it's just a spectacular image. So everyone immediately fell in love with it. It was a good pick.
And the only thing I'm going to add to that is at one of our early JWST conferences, I saw an hour-long talk about the science in just that one picture. There's so much rich science, but we don't have an hour today, so we're going to have to draw it to a close.
I know. I'm sorry that we do have to draw this to a close because your comments have been really inspiring and so interesting. There are many comments in the chat box, which we will share with both of you, and thanking you for your presentation today. Thanks to both of you to being here with us, and we're grateful for you to give back to ARCS by sharing your research and career highlights with us today. We at ARCS are very proud of your success, and we are honored to have supported you when you were scholars. This is what ARCS is all about, and both of you embody why the work that we do is so important. Thank you to everyone for participating in this session. We will send out a link to the recording for you to share with others, and you'll receive a short survey. Please let us know if there is a topic of interest to you. We really do use the survey information to design our sessions, so please return them. Planning for this 2023-2024 year is ongoing. Our next session will be November 8th, 2023 at noon Eastern Time, and will focus on breast cancer. Please look for information on future sessions. Again, thank you so much, Dr. Hammel and Dr. Fox, for being with us today and sharing all your thoughts. And thank you to everyone else again for participating with us. Have a wonderful rest of the day.
Thanks.